What magnetic field is needed to magnetize an iron sphere to its saturation magnetization? Saturation magnetization of iron is 1.69 mega ampere per meter. Assuming that iron is soft, that is to say, the magnetization effects are the only consideration. Okay. So, if we have a soft iron sphere in a magnetic field, so the magnetic field is applied to the left, let's assume, and we have, that means a net north pole distribution on the left side and the net south pole distribution on the right side. So the external field is pointing from north to south. And because we see this net north pole distribution on the left side, this will cause magnetization of this iron sphere so that the south poles will accumulate on the left side closer to the north pole because they're attracted, and the north poles will be attracted to the south poles, net south pole distribution on the right side, so they will be accumulating on the right side. So with that, from south poles to north poles inside, we have a magnetization vector pointing from left to right. And this is going to create within itself a magnetic field. The north poles and south poles will have a field pointing from north poles to the south poles, HD, which is called the demagnetizing field. All right. So let's note these observations. When a magnetic field, remember magnetic field was also called magnetizing force. Magnetic field H is applied to an iron sphere, magnetic surface poles will develop to oppose the applied field H. The opposing field inside, that is induced inside the magnet, is the demagnetizing field. That we show with H sub D. Okay, now what field is necessary to cause saturation magnetization of the sphere? So we need to have an external field that is going to overcome the demagnetizing effects. So to achieve saturation, one has to overcome the maximum possible Dmag field. Okay. And what is the maximum possible Dmag field you can have? H sub D is minus the demagnetizing factor N sub D times the saturation magnetization. This is in SI units. And the demagnetizing factor N sub D is a geometry dependent factor, Dirac factor. The CGS version is 4 pi NDMS, if you remember. Now, we need to calculate this value for the iron sphere. For an iron sphere, the geometrical factor, the magnetizing factor, on the x-axis is equal to its value on the y-axis and equal to its value on the z-axis, because we have spherical symmetry, and these values are 1/3 each. So we have the demagnetizing field equal to minus 1/3 times 1.69 mega ampere per meter. So this gives us minus 0.56 mega ampere per meter demagnetizing field. So therefore, we need to apply an external field that will overcome this maximum possible demagnetizing field. The field that we need to apply is plus 0.56 mega ampere per meter. All right. So this is necessary to overcome the demagnetizing effect and achieve saturation. All right. So to summarize, we're talking about the necessary field to produce saturation magnetization inside an iron sphere whose saturation magnetization value is 1.69 mega ampere per meter. We're assuming that iron is soft and the demagnetizing effects are the only consideration. So when we have the sphere placed inside a magnetic field that is towards pointing from the left side to the right side, we have a net north pole distribution on the left and a net south pole distribution on the right, which induces south poles on the left half of the sphere and north poles on the right half of the sphere. And from south poles to north poles, we have magnetic moment vectors that add up to a magnetization vector, so the total moment per volume. That's the net magnetic moment per volume, pointing from left to the right. And from north poles to south poles, we have a net field that's called the demagnetizing field, HD. And this demagnetizing field has a maximum value minus demagnetizing factor times ms. The minus sign reflects the fact that it is in opposite in direction to the magnetization vector. It's 4 pi minus 4 pi NDMS in CGS. So for a sphere, we have symmetry, so the geometrical demagnetizing factors NdX, Ndy, and Ndz are equal, and these, remember that these should add up to 1, so they are 1/3 each, so the demagnetizing field is minus 1/3 times 1.69 mega ampere per meter. Therefore, we need an external field 0.56 mega ampere per meter to overcome the demagnetizing effects and achieve saturation.